For centuries, the quartzite sandstone pillars of the Zhangjiajie Grand Canyon stood as an impenetrable maze. With vertical drops plunging nearly 1,000 feet into the mist, locals and travelers alike considered this gorge entirely uncrossable. That changed in 2016. Spanning a 1,400-foot gap, a walkway constructed almost entirely of transparent glass now connects the two sides of the valley, suspended hundreds of feet above the canyon floor. The designer, architect Haim Dotan, laid out a strict aesthetic requirement. The bridge could not disrupt the natural landscape. It had to look like a thin white cloud, practically disappearing into the fog and sky. This requirement created an immediate problem for structural engineers. A structure thin and transparent enough to look invisible has almost zero natural mass to resist the mountain elements. Yet this delicate ribbon of glass had to survive intense mountain winds, equivalent to a Category 14 typhoon. Achieving visual invisibility required engineers to take the heaviest, most robust support systems and hide them completely from the public eye. This animated cross-section reveals the first invisible threat. The canyon walls are composed of bedded quartzite sandstone, but centuries of erosion have riddled these cliff edges with subterranean caves and hidden microfaults. Standard concrete foundations poured directly onto the surface would fail. The thousands of tons of horizontal tension from the bridge's cables would simply rip the rock apart, pulling the entire structure down into the valley. To find stability, engineering teams bypassed the surface entirely. They deployed core drills to cut shafts nearly 130 feet straight down into the mountain, reaching the solid, unweathered bedrock far below the cave systems. Heavy bundles of high-strength steel tendons were inserted into these shafts and post-tensioned, effectively clamping the mountain strata together from the inside. This turned the cliff itself into a rock-solid gravity anchor. With the mountain secured, crews began spanning the gorge. Because heavy machinery could not reach the cliff rim, a high-precision drone flew the first lightweight pilot line across the abyss, which was then used to pull the heavy steel suspension cables. By drilling downward instead of building upward, engineers hid the bridge's heaviest support systems deep inside the earth. Once the cables were across, the structure faced a second invisible threat: aerodynamic flutter. Extreme mountain wind shear funnels rapidly through the narrow gorge, creating forces that can twist a bridge apart. Because the bridge stretches over 1,400 feet but measures only 20 feet wide, it has very low torsional stiffness. Without heavy trusses to stabilize it, high-speed winds can cause the deck to oscillate and flutter like a ribbon. This simulation shows the first aerodynamic defense. The steel edge girders are modeled after inverted airplane wings. When wind hits the profile, it generates downward aerodynamic force, pinning the structure in place rather than creating lift. Along the edges of the walkway, open steel grating interrupts the solid deck. These vents allow high-speed air currents to pass safely through the structure instead of building up dynamic pressure against a solid floor. The ultimate defense is hidden directly beneath the feet of the pedestrians. Tucked inside the deck are 7 massive, water-filled tuned mass dampers. When a sudden wind gust pushes the bridge one way, the heavy liquid inside these sealed chambers sloshes in the exact opposite direction. This liquid counterweight absorbs the vibrational energy before it can build into a dangerous sway. By allowing air to flow through the deck and hiding liquid counterweights inside, the bridge manages extreme wind forces without the need for visible steel trusses. With the skeleton secure, the focus shifted to the surface. 99 massive glass panels were installed to create the transparent walkway. This diagram reveals the density of that transparency. Each panel weighs 1.5 tons and is constructed as a 50mm thick matrix, consisting of 3 layers of tempered glass. Aerospace-grade structural ionoplast, called Sentry Glass Plus, bonds the 3 heavy glass panes together. This interlayer is 100 times stiffer than the plastic films used in standard laminated glass, providing immense structural rigidity. To address public fear, engineers orchestrated a brutal stress test. They needed to prove that the transparent floor could survive catastrophic damage without failing. A heavy sledgehammer was swung directly into the deck, instantly shattering the top layer of glass into a spiderweb of fractures. Yet the impact failed to penetrate the layers beneath. The structural matrix remained rigid, even with the top layer destroyed. To prove it, a fully loaded 2-ton SUV was driven directly over the shattered panel, and the bridge didn't show a single microfracture in the supporting layers. This illusion of walking on air relies on aerospace-grade chemical engineering, built to survive extreme, targeted destruction. The grand opening in 2016 was an overwhelming success, but it created its own crisis. 80,000 daily tourists flooded the site, exceeding the design capacity by a factor of 10. The sheer volume of people forced an emergency 13-day shutdown. The bridge itself was structurally sound, but the surrounding local infrastructure collapsed under the pressure of the crowds. During the closure, engineers installed smart digital ticketing portals and real-time IoT load sensors beneath every deck section, allowing the bridge to constantly report its own structural health. The bridge has since become an extreme sports landmark, now featuring the world's highest commercial bungee jump, where participants drop 853 feet into the abyss. Engineers crossed this impossible void, not by conquering nature with heavy steel, but by adapting to its forces to weave a nearly invisible thread across the sky. If you enjoyed exploring the engineering behind this structure, please subscribe and press the bell button for more.